Okay, continuing on with the 2016 10A, we're on problem 18. It was also the 12A problem 14. The last video before this one, in this video, the last problem, problem 17, was filmed at an earlier time when I had different recording equipment, so it might not sound as quality of sound. Apologize for that. Each vertex of a cube is to be labeled with an integer from 1 through 8, with each integer being used once, in such a way that the sum of the four numbers on the vertices of a face is the same for each face. Arrangements that can be obtained from each other through rotations of the cube are considered to be the same. How many different arrangements are possible? This question, in my opinion, it's a little difficult. The reason that it's difficult mostly is because cube numbering vertices, this is not any kind of school math, generally speaking, that you'll do in high school or middle school. You would only encounter this kind of thinking process in extracurricular work or self-study. Maybe graph theory might explain some of this kind of thinking. I can't think of it exactly how it would apply off the top of my head, but that's the only thing I can really think of. So what do? That's the point right there. You might not know the best approach, right? When I solved this problem, to be honest, when I say when I solved it, I mean I submit myself to the test. I take the test under testing conditions, but I don't get a score for it, obviously. I'm well past the age where I can take it. So I started off by just trying to guess. There were some conclusions I was able to make. Not guess, but use like logical progression to get closer and then do a case-by-case basis. But there is later discovered shortcuts that you can find, and if you can find them during the test, it's great. It's a little bit like the Bella and Jen problem from the 2020 test. So in that way. Okay, so how do we get started? First off, if all of the numbers, some of the four numbers on the vertices of a face is the same for each face, if you think about a cube, right, and for me, I'm just going to draw a cube like this. All these lines are parallel, and then this line here will be parallel to this line, and this vertical line is parallel to these vertical lines. You can cut off the back ends if you want. Then do the same thing here, parallel but dotted. Stop when you get level with this, come over there, and come up to this one. So that's the cube I'm going to draw. We could even label it A, B, C, D, E, F, G. Maybe I should for later purposes. So we'll call this A, B, C, D, E, F, G, and H back here in the corner. So if you think about it, E, F, G, H on the back side and A, B, C, D, they're on opposite sides of the cube, and they use all 8 vertices in their composition of the 4 vertices on their face. So the thing is, if all 8 vertices are used, then each of their sums must be half the total sum of the numbers from 1 to 8. So you can do this a number of ways. It's pretty easy to add the numbers 1 to 8. 1 plus 8 is 9, right? 2 plus 7 is 9. You're going to get 4 groups of 9, so you're going to get 36. Divided by 2, each face has to equal 18. This is probably the first conclusion that you need to make to progress in a decently fast pace during the problem under testing conditions. So hopefully when you did it, you were able to get at least this far. I would call it getting to first base probably. Okay, so what next? If each of the faces have to be 18, that's all 6 faces have to have a sum of 18, what can we focus on? How do we think about this? What is a good strategy? For me, it's focusing on extreme values, like 1 and 8, right? Because they're going to have less values, less combinations that they can be involved in, right? So let's see what I'm talking about. If I use 1, I could have used 8 as well as my focal point. I'm going to use 1 as the focal point. So if I use 1, let's go as low as possible. Let's use 2. If I use 2, that's a total of 3. I need a sum of 18, which means I need to use 15. Well, I'm not going to get 15 with any 2 numbers but 7 and 8. So that's it. That's the only way you can get 15 to finish off this set. Then this is a possible face that 1 can be involved in. What's another one? Well, if I change the 2 to a 3, again, you're trying to work systematically, right? Make some kind of an algorithmic process so that you can work through these possibilities faster. 1 and 3 is 4. We need 14 more. Let's again use the 8. We can do it with the 6. So 6 and 8 is 14. Could I do it with anything else without the 8? No, because even the next two largest numbers only add to 13, so they're not going to be possible. So this is the only one that works with 1 and 3. Let's move it up to 1 and 4. Again, keeping the 1 every time because it's more restrictive upon the possibilities available to it. 8 would have the same effect if you wanted to focus on 8 instead. The things that can be combined with it are more restrictive. Okay, so 1 and 4 gives 5. I think it would have the same effect. I'm not 100% sure, but I know 1's pretty restrictive. So 1 and 4 is 5. Maybe explore that on your own. We need 13 more. Let's again do it with 8. So 8 and 5 is 13. And let's do again, there's another way to get 13. We can do it with 1 and 4, and instead of using 5, we use 6 and 7. That doesn't involve the 8. Now, if we go up to 1 and 5, we've in fact already got this right here. We would need to use 12 more. I can't do it with 7 and 5 because 5's already used. I can't do a double 6, so the only other one you could do it with is 8 and 4. And that's what we have right here, 1 and 5, 8 and 4. So that one's already been used. We don't really need to consider it. The same thing is going to happen if you advance to 1 and 6. You'll already have it here and here. And similarly, 1 and 7 is here, and so on. So we don't need to check anymore. These are the 4 ways that 1 can appear. Now, when you think about it, let's place 1 at one of these vertices, right? So I'm going to put it at the bottom down here, 1, right? Now, how many faces get to use the 1 in their combination? The bottom face does, this left face does, and the front face, A, B, C, D, will all use the 1 because each vertex is part of 3 faces, right? So then we need 3 of these to work. And furthermore, what about, we see 1 and 8 is a popular combination. It's in 3 of them. Is it possible that 1 and 8 can appear on more than 2 faces? Well, let's put 8 somewhere. I'm going to put it on the back side back here at H. Then D and H is on this left wall of ADHE, and D and H is on the bottom panel of DCGH. But that's it. It's not on any other faces, and that's because any segment, any side or edge rather of the cube can only appear on 2 faces. So it cannot be that this, and this are all used. That'd be impossible. That would be 3 faces all using 1 and 8. Then what does that mean? It means that 2 of them must be 1 and 8, and one of the faces has to be 1, 4, 6, 7. This is a crucial start to the problem. We can now label, for any such cube to have this property, one of the faces must be 1, 4, 6, and 7. And we'll just label one like this. Right, so if you can't see very well, because the board's kind of small letters written, D is 1, A is 4, B is 6, and C is 7. Okay, well, what happens next? Again, we know that 8 has to be down here at H. How do we know that? Again, because 2 of these, any 2 of these sides must be used. Right? Because we have to have 1 appear on 3 faces, and it's not on this front face. So it must be on the bottom face and the left face, and so because of that, we need that edge. If 1 is located down here, we need that edge to have the 8 on the other end. Further, we can think a little bit more now. This edge has a sum of 9, and we need all the edges, or all the faces, to have a sum of 18. So if this is 9, this has to be 9. And that easily tells us that if we make this 1, 4, 6, 7 with the 8 here, then this has to be a 5 over here. That is E equals 5. Further, now this is 9. In order for the top face to be 18, this must be 9 also. So 6 and 3 would have to go here to make the 9 sum on this edge, BF. Okay? Then again, that's 9. This must be 9 also. There's only one term left. It must be a 2 that goes there. You could write this out. It could be a little tedious to write the letters with the connections every time. So I'm not going to do it. I just wanted you to see where that was going. Okay, so we've got the first one. We'll do Roman numeral style. There's 1. We've got one way to do it. We'll leave it on the board. And as you progress through the problem, you want to maybe start leaving less and less information. We know 1, 4, 6, 7 has to be up here. And once we put it in this exact order with 4 up here, 6 here, and 7 here, all the other values became fixed. We didn't have a choice on them. So let's do this. Let's put 1, and I'm going to put 8. I'm not going to draw the whole cube, right? You don't need to. You need to kind of be able to see the cube in your mind without having to draw it because time is of the essence. Right? So then you're also going to have 1 up here. Let's keep the 4 in place for the 1, 4, 6, 7. We're also not going to label the letters anymore. That was just so we could kind of take baby steps to understand the problem. Again, if this is 9, this face, which is this one up here, will have to be 5. But let's switch the 6 and the 7. Let's put at the top one, and we'll have a bottom one down here. Let's put 7 on this edge and 6 here. Then this will have to be a 2 to make the 9 with that 9, and 6 and 3 will also have to be 9. If you can't see, 1 and 8 is this one, 4 and 5 is this one, 7 and 2 is the upper, and 6 and 3 is the lower. Further, maybe you want to check other things like, are all the faces actually 18? We know that the front face and the back face are obviously 18. Because these edges are all 9, all of the faces going around this way must be 18. The only question would be, are the top and bottom 18? Actually, that's not even the case. Yeah, we've got it. We know they're all 18 because this goes around the outside and we have the back and the front face being 18. So we can be satisfied. Furthermore, this cannot be rotated to make this, right? We still have the 1 and 8 on the bottom, right? 4 and 5 is up here, but there's no way to rotate it where these two edges switch. It's not possible. So we can be confident that this is now a second way. Now we're not going to get any more by switching 6 and 7 again, so we're going to have to swap out this 4. Again, you're trying to work algorithmically, some kind of process which keeps as much of it intact as possible while you move to the next one. I'll call this 1 and this 2. Let's do 3 now. Again, we'll start with the 1 and 8. That being the bottom panel. But on the upper edge right here, we're not going to put a 4 this time, we're going to put the 6. And we know that since this is 1 and 8, that's 9, this also has to be 9, that will have to be a 3. And this is the upper right edge, and this is the lower right edge. Furthermore, since this is 1 and 6, we need 4 and 7 to appear at these two vertices. So I'm going to put the 4 here and the 7 here. It doesn't really matter right now because it's a fresh kind. So then again, because this is 9, this over here also has to be 9. So 4 and 5, 6 and 3, that's these two edges, A, E, and B, F. Okay? Then obviously all that's left is 2. 9, 9, 9, 9, we're golden. And furthermore, you cannot rotate this to achieve the others, which you should be checking as well. For one thing, to do this one, you're going 1, 6, 4, 7 when you start from the 1 going either direction around. I cannot get 1, 6, 4, 7 on this one. I have to cross over the diagonal of the cube from C to A to make to the 4. And same here, 1, 6, 4, 7. That's not going clockwise or counterclockwise around one face of the cube. So this is a unique solution. Okay, let's do another one. That's the third one. We've got 3 now. Let's do the fourth one. Again, you want to keep the 1 and 6 intact. So 1, 2, 3, 4. This will be 1 and 8, and this will be 6 and 3. But instead of putting the 4 on top and the 7 on bottom, let's put the 7 here and the 4 here. We're going to switch them. All right, and so then obviously these have to be, these edges for every single one of these has to add up to 9. That's what we learned early on. That streamlines this process to go a lot faster. You should be getting faster as you go. At the start, you might not be very fast because the reasoning is very foreign. But as you progress through the problem, it becomes more and more familiar, and you're able to speed up the process, maybe getting this problem done in 5 minutes, maybe, depending on how quickly you came up with a strategy to target one of the extreme values like 1 or 8. Okay, so that's the fourth one. Let's look at a fifth one. 1, 2, 3, 4. Again, the same thing, right? Okay, so 1 and 8, we're going to keep it here. It does have to lie on one edge. And then what about these here? Keep in mind, by the way, the original problem does not have labeled vertices. That's our invention so that I could explain it to you, basically. So don't assume that, if I put the 1 and 8 up at A and E that it's going to be different. It'll just be a rotation of one of these. Okay, so 1 and 8 goes here. We've done one with 6 and one with 6. Again, that's this being a 1 and the A being a 6. We've done that. We've done one with 4 and one with 4. All that's left is one with 7. And since 1 and 8 is here, this must be a 2. We now have to place the 4 and the 6 on one of these two edges. And again, just randomly pick them and progress. 4 with 5, 6 with 3. There you go. Now, I can hit 1, 6, 4, 7. Can I do that here? 1, 6, I have to cross over 1, 6, 4, 7 like that. That's not the same thing as going around clockwise or counterclockwise. This one does have 1, 6, 4, 7, but the other side goes 8, 3, well, it does do 8, 3, 5, 2. Is this a rotation of this one? No, I don't think it is. If I was to rotate, yeah, there's no way to get 7 and 2 to be above. It'd be like this 7 and 2 appearing up on this edge, keeping the 1 and 8 in the lower left. There's not going to be a way to do that unless I switch the 1 and 8 to be backside. So 1's back there and 8's over here. Yeah, I don't think it's going to work though. So this should be a unique solution as well. Okay, so then let's go to the next solution, which again is just going to switch these two. And you can see that you're going to get 6 solutions. If you switch these, you just switch these two edges, right? So how can we be, one more time, I want to just be very sure that these two are not a reflection of each other. If it'd be like putting the 1 and the 7 up here, right? That's this one. But this one has the 7 down here on the lower one. I just don't see any way that you can achieve that with a rotation of the cube. A reflection maybe, but not a rotation. Yeah. So you're going to get 6 solutions. That's going to be the answer. Again, it's a little funky reasoning. That's par for the course. You're probably going to get about 2 or 3 funky reasoning problems per year on every test. Maybe more than that. You know, at least 2 or 3 that are just weird, kind of never thought of before concepts. All right, on to the next problem.